Hello students and welcome to 12th Standard Physics, 2nd PUC Physics. In this video lecture, let us cover lenses, types of lenses, refraction through lenses, lens maker formula. A lens is an optical device which has at least one spherical surface. For example, this is a sphere. This is another sphere. Now observe, this region is bounded by two spherical surfaces. So this is a lens, or if this is a spherical surface, this is a plane surface, then this is a lens. This shaded region is a lens. If this is a sphere, this is another sphere. If region between these two spheres is filled with some liquid, suitable liquid, then this region forms a lens. So at least there should be one spherical surface. Now depending on the number of spherical surfaces, lenses are classified. So this type of lens biconvex lens. If a lens has two concave surfaces, biconcave. This is a plane and this is a convex surface, plano-convex. This is a plane, this is a concave surface, plano-concave. Then if there is a convex and the second surface is also convex, then this is convex concave. This is concave and this is convex. Convex concave. Sometimes it is also called concavo-convex. Okay, so let us call convex concave lens. So these are different types of lenses. Now to find focus and focal length in the case of convex as well as concave lenses. So this is a biconvex lens. This line is the principal axis. Principal axis is that line which passes through center of curvatures of these two surfaces. Now, if there is a ray of light along the principal axis, after refraction without deviation it passes straight like this. Let me consider another ray close to the principal axis and parallel to this, which is called paraxial ray. So this paraxial ray, students, make sure that you draw the incident ray till principal section. Principal section is this imaginary line. Okay. This paraxial ray, after refraction, passes through a point on the principal axis, something like this. Another ray, paraxial ray, after refraction, passes through the same point. So this point is the focus, denoted by capital F, focus. And distance of the focus from principal section of the lens, that is this distance, is called focal length, denoted by small letter f. So this is how we can find out focal length of a lens. So in the case of convex lens, this is a ray along the principal axis, refraction, but there is no deviation. Refraction means change in speed. Okay. Now let me consider second ray close to the principal axis. Draw incident ray till principal section. Let me consider another ray. Ray is drawn till principal section. I'll just change the color of pen. After refraction, it diverges, and the diverging ray, this ray, refracted ray, emergent ray, appears to be coming from some point on the principal axis. So this is the refracted ray. In this case, this is the refracted ray because the ray is along the principal axis. If you draw dotted line, produce it backward, that passes through this point. Now consider the third ray. You have to draw diverging ray such that it should be from the same point. It should appear to be coming from the same point. See, this lens diverges the rays after refraction. That is why concave lens is called diverging lens. This is convex lens or converging lens because after refraction the rays converges through a point. Don't forget to draw arrow mark. So if rays parallel to principal axis and close to it passes through a convex lens, then after refraction they converge through a point. That point is called focus, and distance of the focus from the principal section or optic center. So this is called the optic center. Distance of the focus from the optic center is called focal length, denoted by f. So in this case, this is the optic center, this is the focus f. So distance of the focus from the principal section, that is this. This is focal length, focus, focal length. Recall what we have learnt in concave mirrors or in convex mirrors. After refraction, if the rays converge through a point, then that forms a real image. After refraction, if the rays diverge, then that forms a virtual image. So this gives virtual image, this gives real image. Students, you have to copy these diagrams, write everything using pencil, scale and label suitably. Don't forget to draw arrow marks. Make sure that you don't take more time to draw these diagrams. Maximum 1 minute. Okay. Now, formation of images using convex lens. This is a convex lens, principal axis, and on the principal axis, let me mark 2 points at distances say 4 centimeter and 8 centimeter. Okay, this is the optic center. This is focus F, and this is twice this distance, so it is 2F. Let me keep an object within F. So this is a linear object within F. Okay. O is for object. So in this case, object within F. Let us see how to get image of this object. If this is F and 2F, on the other side also F and 2F at a distance 4 centimeter, at a distance 8 centimeter. So this is F and this is 2F. Consider a ray along the principal axis, means from the foot of this object. This ray is passing through the optic center and along the principal axis, so it should travel straight. There is no deviation, but there is refraction. This is the refracted ray. Now let me consider second ray parallel to the principal axis and close to it. So this is second ray. Make sure that the ray is drawn till principal section. So if you draw this line, so this line is the principal section of the lens. Okay. Since this is parallel to principal axis, after refraction, this should pass through the focus like this. This refracted ray should be from the principal section. Now let me consider another ray from the head of the object. If that ray is passing through the optic center, then it travels straight like this. If you observe, these two refracted rays are diverging. Diverging means they appear to be coming from some point. So let us find that point by this dotted line. Using the second ray, dotted line. So these two dotted lines will meet at this point. So this is the position of the image. So I stands for image, O is object. What is the nature of the image? This is the object. After refraction, the rays are diverging, means this is a virtual image. Nature of image, virtual, image is bigger than object, so magnified, and this is erect. The image is not inverted, it is erect. Virtual, dotted line, magnified, bigger, and erect. It is not inverted. It is not upside down. So this is the nature of the image when object is within F. Students, accidentally I am getting this image close to the focus. That doesn't mean that every time you should get image close to the focus. This image can be anywhere. Okay, image can be anywhere, but this should be bigger than this object. Now in this case, let the object be at F. Convex lens, principal axis. So let me keep 8 centimeter at the optic center. So 4 centimeter, 8 centimeter, F and 2F. On the other side also 4 centimeter and one more 4. So here to here 4, here to here 8 centimeter. This is F, F to F, F to F. So this is F, this is 2F, F to F. Let me write that later. If this is an object on the principal axis at F, this is a linear object. This is a ray along the principal axis. From the foot of the object, there is refraction, but there is no deviation, bending. Second ray, parallel to principal axis. Draw incident ray till principal section. Again, principal section is this imaginary line. After refraction, since this is parallel to principal axis, after refraction, it should pass through the focus. Now let me consider another ray from the head of the object passing through the optic center. If you draw carefully, then these two refracted rays will be parallel to each other. Parallel to each other means they never converge on this side or on the other side. When everything is over, you can write F and 2F. F, 2F, just like F and 2F. So what is the nature of the image? Image is at infinity. That is enough. Image at infinity when object is at F. Now third case, when object between F and 2F. Object between F and 2F. Lens, principal axis. Let me note down F and 2F. F, 2F. Let me consider an object within F, between F and 2F. This is a linear object. This is a ray along the principal axis. refraction without deviation. This is another ray parallel to the principal axis. Again, draw till principal section of the lens. This imaginary line is the principal section. After refraction, this ray should pass through the focus. Now another ray from head of the object passing through this optic center. Since this ray is passing through the optic center, there is no deviation. So it passes straight and it meets the first ray somewhere here, and this is the image. Image of this object. Observe, this is a ray from the foot of the object from the foot of the object. So this foot appears here. Head, from the head, these two rays converge at this point. So this is the head. So the image is inverted. Also observe height of the object and height of the image. It is magnified. And the image is due to converging rays. Image is due to converging rays means it is real. So real image, magnified, and inverted. Now after completing the diagram, let me write F1 to F. Now object at 2F. This is fourth case. Lens, principal axis. Let me note down F1 to F on either side. 4 cm, 8 cm, 4 cm, 8 cm, F to F. Let me keep object at 2F, linear object. So this is linear object. A ray from the foot of the object along the principal axis travels straight. So there is no deviation. Second ray, from the head and parallel to the principal axis. Again, draw the incident ray till principal section. This line is the principal section. After refraction, this should pass through the focus. Next, from the head passing to the optic center. After refraction, it should travel straight. Then this is position of the image. So this is object O and this is image. Here height of the object equal to height of the image. Inverted, this image is due to converging rays. Therefore, image is real, inverted, and magnitude of magnification equal to 1. Magnitude of magnification equal to 1 means height of the object equal to height of the image. So these are incident rays, these are refracted rays. This is the image. Now, fifth case, when object beyond 2f. Object beyond 2f. Convex lens, principal axis, f, 2f, f, 2f. Let me keep the object beyond 2f. This is a linear object. This is f, 2f, f, and this is 2f. A ray from the foot of the object and along the principal axis. It travels straight. Another ray parallel to the principal axis. This is principal section of the lens. After refraction, this ray should pass through the focus like this. From the head passing to the optic center. Since it is passing through the optic center, this should travel straight. There is no deviation. So this second ray meets the first ray at this point. So there forms the image. So this is image, object, this is f, this is 2f. Students, please note, you may not get image between f and 2f every time, okay? But make sure that this image is at the intersection of these two refracted rays. And you can see this image is diminished, size is less than that of the object. So nature of image diminished, inverted, and then real. Diminished, inverted, and real. Real is due to converging rays. Inverted, inverted. This is head, the head is upside down. Diminished means size of the object less than, size of the image less than size of the object. Optic center. This is principal axis of a lens. This is for principal section. Students, you can draw lenses using bangles or any objects like this, okay? This is a convex lens. This is incident ray on the lens. So this incident ray, when it encounters interface of air and glass, if it is a glass lens, then it undergoes refraction. It undergoes refraction, and if it passes through this point, then the emergent ray will be parallel to the incident ray. So with respect to incident ray, this emergent ray is parallel, so there is no deviation. If that happens, then the refracted ray inside the lens meets the principal axis at some point, and that point is usually denoted by O, and that O is optic center. So what is optic center means? It is a point in the lens on the principal axis when a ray of light passing through it remains undeviated, means this is parallel to this. So this is the optic center. Next, magnification. Magnification equal to ratio of height of the image to height of the object. Okay. If this is a lens, principal axis, this is the object, and this is the image. We don't know the position of object and position of the image. Okay. If height of the object is 1 unit, this height is 3 unit, then magnification equal to height by height. 3 times, 1 time. So I am not using Cartesian sign convention here, just to understand. Okay, this is height of the image. I stands for image, O stands for object. So 3 by 1. 3 by 1 is 3. So this 3 is dimensionless quantity. Dimensionless. So it has no unit. It is just a number. This says the image is 3 times the size of the object. If magnitude of magnification is half, then image is half the size of the object. That's how the magnification is used. Okay, go through this statement. Magnification is the ratio of size of the image to size of the object. Principal axis, principal section, convex lens, this is incident ray parallel to the principal axis. Since it is parallel to principal axis, after refraction, the ray should pass through the focus. So this point is the focus, denoted by F. This is direction of incidence. Let this angle be delta. If this is delta, then this angle is also delta. Distance of the focus from the principal section. This distance is focal length, denoted by F. Let me consider this height, distance of the incident ray from the principal axis. let this height be h. So tan delta, tangent of this angle, tan delta equal to tan delta equal to opposite side h by adjacent side. Adjacent side is f. This is f. If h equal to 1 meter, then tan delta equal to 1 by f. And this 1 by f, which is equal to tan delta, is a measure of power of a lens. Power, fine. Don't worry about the pronunciation, okay? Power of a lens. So power of a lens is reciprocal of the focal length. Power of a lens is tangent of the angle by which the lens converges or diverges. In this case, converges a beam of light falling at unit distance, because we are keeping h equal to 1, falling at unit distance from the optic center or principal axis. Go through this statement and the steps. So tan delta, which is equal to power. So SI unit is diopter. This diopter is dimensionless. As you can see, it is h by f. H is in meter, f is in meter, means it is a dimensionless quantity. Power is a dimensionless quantity. Go through this statement. Power of a lens is the ability of the lens to converge or diverge the ray of light. It is the reciprocal of focal length in meter. This focal length should be in meter. Okay. What is the definition of power of a lens means? Power of a lens is defined as tangent of the angle by which lens converges or diverges a beam of light falling at unit distance from the optic center. So this is the optic center O. Now, first focal length and second focal length. If this is a lens, this is principal axis, this is incident ray. After refraction, if the ray is parallel to the principal axis, then this point is called first focal point. So first focal point is that point which is towards the incident ray or rays. Okay. And corresponding distance from the principal section is called first focal length, f1. Now second case, this is a lens, principal axis, this is incident ray parallel to the principal axis. After refraction, it passes through a point. Then this is the second focal length, second focal point or second focus, and the distance of second focus from the principal section is second focal length. Focus on the same side as the incident rays is called first focus. Focus on the same side as the refracted rays is called the second focus. Corresponding lengths are called second focal length, first focal length. And surprisingly, f1 equal to f2. These two lengths are same. Lens maker's formula. This is reference line. Biconvex lens. A, B, C, D. In the absence of ADC. And in the presence of ADC. Students, make sure that you draw all these diagrams one below the other with respect to this line, reference line. In the absence of ADC, in the presence of ADC. So convex lens is bounded by two spherical surfaces, convex surfaces. Now, let us see refraction through this lens. Principal section, principal axis, let O be a point object. From this point object, a ray of light along the principal axis passes undeviated. This ray is also passing through the optic center, therefore there is no deviation. Another ray from the object incident on the lens, like this. This ray should undergo refraction, bending. When it interacts with interface ABC, due to refraction, it bends like this. This bending is due to interface ABC. Because of second interface ADC, again the light ray bends. So this is the image I of this object O. Now, in the absence of ADC, this light would have traveled straight and met the principal axis at this point, I dash. Understand? This light ray undergoes refraction because of ABC. If there is no ADC, then this light ray would have traveled straight, which could meet the principal axis at I dash. But because of ADC, again it undergoes bending and meets the principal axis at I. Now let us understand all these things in two steps. This is object. So this is for the object O. Ray along the principal axis. Ray along the principal axis. So this looks like refraction through a spherical surface, isn't it? There is a spherical surface. If this is a glass lens, this is glass. Second ray, keep this distance same in the second diagram. So this is the second ray. Because of ABC, because of ABC, A, B, C, spherical surface, this ray bends, and before bending we should draw the normal, isn't it? Let this be C1. Center of curvature of this spherical surface, and this is normal drawn at the point of incidence. The light ray is traveling from, say, rarer medium to denser medium. Rarer to denser bends towards the normal. So let me show bending. This is the reference point. So the light ray meets the principal axis at I dash. So this is I dash. Understand? Incident rays, diverging rays means real object. Because of converging rays, real image. Real object, real image. Now, when this light ray is traveling, it encounters second interface, ADC. ADC. Let me draw this ray along the principal axis. So this is the ray along the principal axis. No issues. Identify I dash. I dash. This is reference I dash. From I dash to A, nothing but this point. Draw a dotted line. For the second interface ADC, let this be the center of curvature, C2. From C2 to this point. Time being, treat this point as the point of incidence. So this is normal drawn at the point of incidence. Okay. Now observe this refracted ray, which meets the principal axis at I. So this is I, this is I. Let me draw the emergent ray. Incident ray, refracted ray. Incident ray, refracted ray. Incident ray at the second interface, ADC, and this is the emergent ray. This is the incident ray inside. This is the incident ray inside glass. See, air, glass. Air, glass. This ray is inside glass. So this ray is inside glass. So after refraction, it cuts the principal axis at I. So this is the final image. This final image is obtained due to converging rays. Therefore, this is real image. Now, whatever I write, that is for your reference. Okay. This is real object, real image. This is final real image. This real image, is due to this virtual object. This incident ray when it is traveling in air undergoes refraction because of spherical surface ABC. Meets the principal axis at I dash. No issues, right? Real object, real image. But when this ray is traveling inside glass, see, compare. This ray is traveling inside glass. When this ray is traveling inside glass, it undergoes refraction due to ADC. So this ray appears to be coming from this point. This ray has not reached I dash, but this ray appears to be coming from I dash because instead of going there, it is coming to I. Instead of there coming to I means this is virtual object for this real image. This is virtual because ray has not traveled to I dash. Okay. I think this virtual object has come for the first time, isn't it? Doesn't matter, you'll get used to it. Let N1 be refractive index of the surrounding medium and N2 is refractive index of the glass N2. So in this case, N1, N2 is refractive index of the spherical surface. N2 refractive index of spherical surface, outside is N1. Distance BC1 is R1. Radius of curvature of first surface is R1. This is object. Object to pole is object distance. So this distance is object distance. This is U, object distance. D to I, this is the pole for the second interface. D to I is image distance. So this is image distance. V. This I dash is virtual object, isn't it? So D to I dash. Let this be V dash. So same thing here. Object to B is U. So this distance is U. B to I dash is V. This is V dash. See V dash. V dash is D I dash. Here B I dash. If it is a thin lens, distance BD can be neglected. If BD is neglected, then B I dash is equal to D I dash. Okay. B I dash is approximately equal to D I dash. That is why this is also V dash. Now in the final case, virtual object, pole. So this distance is V dash. See, D I dash is V dash. D I dash is V dash. D I is final distance. Final distance is V. V. Okay. Now let us write the statements. Consider a convex lens of focal length f. Let R1 and R2 be the radii of curvatures of ABC and ADC respectively. So this is R2. This radius of curvature is R1. Be careful, there are so many parameters. Okay. Let N1 and N2 be the refractive indices of the surrounding medium and the lens respectively. Let O be a point object on the principal axis. About this ray. A ray from O along the principal axis passes undeviated. About this, another ray from O close to the principal axis undergoes refraction and cuts the principal axis at I. So this is the path where I is real image of the real object O. Here I is real image of the real object O. Now, in the absence of ADC, that is, come to the second diagram. In the absence of ADC, I dash is real image of the real object O. In refraction through spherical surface, we have this expression. In one of the steps, we get N1 by object distance plus N2 by image distance equal to N2 minus N1 by radius of curvature. This is not the final expression. Okay. Students, please pay attention. This is not the final expression. Just before final expression, we get this N1 by object distance plus N2 by image distance equal to N2 minus N1 by radius of curvature. Now N1, refractive index of object space. This is the object space because incident ray is in this space. So it is N1 by object distance is OB plus N2, refractive index of image space, by image distance BI dash equal to N2 minus N1 by radius of curvature. This radius of curvature is BC1. Let this be equation 1. Now, in the presence of ADC, I is real image of the virtual object I dash. Here also, let us use the same formula. Object distance, N1 by object distance, refractive index of object space. This ray is inside N2. Therefore, N2 by object distance. This di dash is the object distance. Plus image space. Refractive index of image space is N1. N1 by image distance. Image distance is di equal to N2 minus N1 by dC2. dC2. Students, you have to understand a small point here. This di dash, in this diagram, di dash, virtual object means the light ray appears to be coming like this and reaching I. It appears to be coming like this means this direction is opposite to di dash. All distances are measured from D, from the pole along the principal axis. Distance is measured from D, but light ray appears to be coming from I dash. See, appears to be coming from I dash. Distance, these two directions are opposite. That is why we have to write negative sign here. This is equation 2. Refraction through first surface plus refraction through second surface is the refraction through the lens. Therefore, we have to add these two equations. This di dash is approximately equal to bi dash. So bi dash is approximately equal to di dash. When we add these two equations, this is with plus and this is with minus, get cancels. We are left with N1 by OB plus N1 by di. Sum of these two. N1 common factor, N1 common factor, one by OB plus 1 by di equal to, here N2 minus N1 is common factor, 1 by BC1 plus 1 by dC2. Take N1 to the other side. So 1 by OB plus 1 by di equal to, take N1, bring it down below N2. So it is N2 by N1 minus N1 by N1, N1 by N1 into 1 by BC1 plus 1 by DC2. This is nothing but N21, refractive index of second medium with respect to first medium, minus 1. N1 by N1 is 1 into 1 by BC1 plus 1 by DC2. Now applying Cartesian sign convention, one by OB from the pole to left side. So 1 by from the pole to left side means distance is taken with negative, object distance, plus 1 by DI. DI, I is to the right of D, positive x-axis. Therefore plus V. Students, I hope you understood this. OB from B to O. DI from D to I. Distances are measured from the pole. Therefore positive. Equal to N21 minus 1 BC1. BC1. With respect to this pole, this C1 is to the right. Right is taken with positive. Plus R1. Plus 1 by DC2. DC2. With respect to D, C2 is to the left. So minus R2 equal to N21 minus 1 1 by R1 minus 1 by R2. Left hand side 1 by V minus 1 by U. If object is at infinity, here is a tricky part. If object is at infinity, then image distance equal to focal length. Object is at infinity means object distance is infinity, minus 1 by infinity. Image distance is f, 1 by f, equal to, let me write this as it is, N21 minus 1 into 1 by R1 minus 1 by R2. What is the meaning of object is at infinity? Then V equal to f. If this is the lens, this is the lens. Object is at infinity means the object gives parallel beam of light like this. When incident rays are parallel to the principal axis, after refraction they pass through a point. So this point is focus and this is the image distance, which is equal to f. So V equal to f. That is what we have written here. Therefore in this expression, this 1 by infinity is 0. Therefore 1 by f is 1 by f equal to N21 minus 1 1 by R1 minus 1 by R2. This is the required expression. This formula is called lens maker's formula, because once the type of material whose refractive index is known, if R1 is fixed, then one can calculate R2 to match this focal length, because focal length will be given by eye specialist. The manufacturer, lens maker, will be using glass of refractive index, so he knows the refractive index. he will fix R1 and he will identify the second radius of curvature R2 using this formula. In that sense, this formula is called lens maker's formula. And here, if you observe carefully, instead of 1 by V minus 1 by U, we have 1 by F. One by V minus 1 by U equal to 1 by F. So this is called thin lens formula. So this is thin lens formula and this is lens maker's formula. Students, in your syllabus you have derivation of this and not thin lens formula. Okay.